มื่อกี้มัน
ได้
ตก
อยู่
ไป
นะ
หน่อยใช่เห็นอาจารย์พอดีครับ
อันนี้ระยะนี่มันขนาดไหนมันจะได้ไม่ตกเฟรมอ๋อกว้างอยู่นี่กว้าง
ใช่ครับเมื่อกี้มันขอบตรงนี้เลยขอบฉากเลย
อ๋อระยะประมาณนี้โอเคงั้นไม่แตะตัวนี้นะ
ครับ
อย่างนี้เราสามารถเล่นอย่างนี้ได้ปะ ได้ใช่ไหมจะได้ไหมเนี่ยต่อโอเคอดไม่ได้อะอดไม่ได้ Let's come back to the steps in olefin polymerization. Like I said, no. Okay, I ended here. Okay, we ended here. So there are many steps in olefin polymerization. Okay, the setup itself of the ligand structure is like we have ligands, we have metal, and normally we would have two initiating group. Okay, one group will be removed, and then you get a positive charge, and this group will be initiating the polymerization. I will explain more detail later on. Okay, and here are some example of these groups. Normally the metal is in group 4, so titanium, zirconium, and hafnium. And ligands can be so many things. Alright, there are 4 steps in olefin polymerization: activation, initiation, propagation, and chain transfer or initiation. It's like this. We have this is CP. Okay, CP. So you have structure like that. First one is activation. Activation. The MAO here abstract the metal, the chloride here, and change the chloride into the metal group with the vacant side. Okay. After that, we have the R group. R group here coordinates to the empty side there, and then metal attack. So you initiate it, and then after that you have propagation, because this process repeat over and over. So you get polymerization to get the polyolefin. Let's take a look into one by one. The activation. There are many activators on the market. BAF, tritium-borate, MAO, the one I just mentioned, trialkyl aluminum, for example. But the main objective is like this. This group will draw or abstract this metal group. Okay, take this metal group away. What is the charge of the metal group normally? Okay, imagine when we have metal and carbon atom. Okay, which one should be positive? Which one should be negative? Can you guess? Which one should be the positive? Metal, right? Normally metal is positive most of the time, right? So when we have metal carbon bond like this, C is normally it's like a negative charge, like methyl group, methyl negative. So if you remove this part out, the metal will be positive, right? And the next step will be coordination. You have the double bond. The double bond contains electrons, right? So that means if the metal is positive charge, the double bond will like to coordinate, right? So that means if we make this a positive charge on this empty side here, double bond will come in and coordinate more efficiently compared to something like this. This is not good, right? This is not good, but this is much better. We have a positive charge there. Okay, and C, this is not chloride. Okay, this is Ci. It means like the counter ion. Because you remove this part will become a counter ion. I'm sorry, you remove this part, it will become the counter ion. Okay. A lot of people, students in previous year, they thought this is chloride, and they got confused. How come you get chloride? You add this, and where is chloride? So it's counter ion, Ci. Empty side for alkene coordination. All right, here are MAO. Like I said, we have trimethyl aluminum. You add water, and then you get MAO. And right now there are so many structures of MAO, depending on how you prepare them. Okay, for example, you have trimethyl aluminum, and then you just add water as a drop. You get one type of MAO. You can spray as a vapor. You get another type. At low temperature, at high temperature, at what solvent, different kind of this will give you different type of MAO, really. So there are many recipes, like I said, to prepare MAO now. A lot of them will be very good to the polymerization. Okay, but the main thing for this is when you add water in there, water will replace 2 methyl and to become ethane, and then you will link between oxygen and aluminum, oxygen, aluminum like that. And you have free methyl group. See, you have free methyl group there. The methyl group will replace the chloride and give you this as the active species. Okay. Remove chloride out. It can pass through the methyl chloride exchange first like this. So you get chloride, change into methyl. Next step, MAO can also abstract this chloride and give you that one. But this is the active species that will start the polymerization. Okay. Like I said, MAO there, you can also modify MAO with other techniques, other variation. I don't need to go into detail about this, but just to let you know that MAO, the basic one will be you add water into the trimethyl aluminum, but there are so many variations. You can even make it, exotic later on as well. I'll show you. Another activator is the borate, like this. This is tris pentafluorophenyl borane, okay, or boron. Tris pentafluorophenyl borane, FAB, or some people call BARF, BARF. Okay. It's the same compound. This is a highly Lewis acid site at boron. So what happened is the methyl group is now transferred to the boron like this one. So you get, this is the counter ion, and now zirconium is zirconium plus, and ethylene can come in and coordinate, and that's the same type of reaction. There are many variations now that you can modify the boron compound. Here are some synthesis. Don't worry about it, but I just want to show you that this compound, if you do a lot of variation, that's quite expensive borane actually. You may get higher activity, but still expensive to do so. Okay. When you remove methyl group to get positive charge and an empty site like this, what really happened is, but the methyl group here is actually not clear cut. It's not removed 100%, but it's like staying between zirconium and the boron, still stay in there. Just like, I want to grab you from TQ, but you don't want to leave TQ, so you kind of hanging in between, just like that TQ say, no, go away. See, that's what happens, because BARF is like it's still, because proton is small, okay? So carbon can bridge between metal and the boron. It's like, it doesn't go anywhere, still stay around. But if you have olefin comes in, this can be replaced with ethylene to do the coordination. All right, so if you have this situation, anything with double bond can come in and coordinate, like a solvent, amido, anything, that can also coordinate as well, like competitively. But to solve the problem, like I said, the one that I mentioned between Nin and TQ here, see? If this group is still hanging nearby zirconium, the activity will not be very good, right? Because basically the whole group here is blocking the monomer. Okay? So people solve this problem by, okay, why not we change to a trityl borate activator? It looks something like this. The borate is like a C6F5, but not 3 of them, but now they have 4 of them. So this group will be non-coordinating. It cannot coordinate to the metal. It's like a big bulky group of a negative charge. So the job is the trityl group will react with the metal group and give you a perfectly like a positive charge. With this group as the bulky group, it looks something like this. Trityl abstract the methyl group there and give you a positive zirconium cation, and the anion will be big bulky group there. Okay, so this gives you more activity to the catalyst. Now the initiation, comes in, monomer comes in and then coordinate. And what happened is the methyl group attack double bond here, double bond flip there, and then you get the inserted product. All right, and several reactions takes place the same way, and then you get this kind of thing. All right, chain transfer, I don't want to go into detail very much, but it's a common pathway for decomposition is the beta hydrogen elimination. when you look at the alkyl group in organometallic compounds, if you have beta proton, this is the alpha position. Okay, this is the metal. This is alpha position. This is beta position. The proton at the beta position can be removed easily. We call beta hydrogen elimination. It gives you, this is transfer to metal, right? And then you get the double bond flip back like that, so you get a double bond there. And then this double bond is removed, so at the end you get metal hydride. So that's the side reaction that occurs a lot. Okay, don't worry about this. All right. One thing about olefin polymerization that, as I mentioned earlier, it is the stereoselectivity. Because cyclic catalyst does not provide selectivity, only the metallocene based chemistry. So I'll focus on that from now on. Okay, there are two types of stereo control. The first one we call the ligand control, and another one we call the chain end control. What it means is, another name is enantiomorphic site control. It's the same thing, just different name. It's like this. Imagine okay, imagine I am the catalyst, okay, like this one. The catalyst sit here, I am the ligand surrounding the catalyst. This is the big bulky group, which is, my hands over here. If I have two hands like this, the monomer can come in either this way or this way, right? It's the same thing because it will hit my hand here for sure. But let's say in some case, if I have the ligand that has only one arm over here, this is more available. This is more bulky. So the ligand, the monomer will come in and we'll see that, okay, bulky group on this side, I don't want to come here. Maybe coming from this angle is much better, right? So that it will come on this side rather than on this side. This is how we control the reactivity using the ligand, basically. That's why we call ligand control, because the ligand will control the reactivity, selectivity of the monomer. Okay, we'll see later on what happens, what I mean by that. Okay, all this selectivity will come from the ligand control. Before I go on, let's take a look at the structure of the catalyst first. Let's take a look at some nomenclature here. Okay, this is the metal, all right? Remember I told you two methyl group in olefin polymerization in the catalyst. This is the two methyl group hanging up front there, and the back there, that is the ligand. Okay, it will look something like, you see metallocene is like CP here, right? It's wrapping like that. This is the like the shell, phá hoi. It's just like a shell like that. We have metal in there, and then dimethyl here, left and right, which is this one right here. This is how we view. You are looking at the shell, through this way. It's like that. And from this, you can tell the based on this the catalyst structure. Actually, you can tell the point group a little bit, because from this one we only have C. Well, forget about the group here. Only the ligand framework. This is a C2V structure. If you don't know what that is, don't worry. Okay, it's just some name that we give to the symmetry. This is CS structure, and so on. C2 site control, C1. Oh, never mind. I think a lot of people will get confused, but never mind. Let's take a look in the next one. Now we'll see how we can control the catalyst, okay, selectivity. Like I said, we have, this is the growing polymer chain, okay, this is the empty side. Ethylene comes in and coordinates, right? And when it coordinates, it will polymerize. So let's take a look at this one first. Now, from this, I think you can understand that this empty side is up front, right? And the dashed line here, the R group is on the other side, right? Now, look at this carefully, okay? I'm looking at this direction. This is what I'm seeing, okay? I'm looking at this direction. This is what I'm seeing right now. We have the CP on the back. We have this methyl on the left-hand side. We have the R group there on the polymer chain, P on the polymer chain there. on the right hand side. Do you follow me at this point? Okay. If you don't follow, please raise your hand. This is very important. We are changing the angle. I'm looking at there. Empty on left hand side, polymer on the right hand side. I just turn my head in this angle. This is what I'm seeing. Empty side, polymer side. Okay. Now, the point I want to make on this slide is if you have double bond coordinating to the polymer, okay, like this. Coordinating to the metal like this. What happens is the polymer chain attacks the double bond, and after it attacks the double bond, the whole polymer chain will be swing to the left hand side. Okay, see, because this thing attacks, so it jump to this side, so you will get polymer chain on the left hand side and empty side over there. Okay, imagine I'm the metal, like two hands like that, right? And empty side here.ขอ4 หนุ่มมาหน่อยขอ4 หนุ่มลงมานี่แป๊บหนึ่ง TQ นะOkay. I want to show you something. Okay. You are the LQ group. You are the LQ group there. So I am the metal in the center, right? Okay. So right now we are at this stage here. This is the polymer chain, right? And the empty side is here. So what happened is, olefins come in, you come in, coordinate with me here. And what happened is the R group here attack the double bond, right? So it attacks the double bond, form a new bond. So this is empty now. And now I form a new bond over here. So you can see that the chain swing to this side, right? Empty. The new monomer comes in, coordinate with me here. Okay, come in closer, coordinate with me here. But the R group, which is not him anymore, but this group here, attack TQ there, form a new bond, right? Now this is empty, so I form a new bond, LQ there. The next monomer comes in, coordinate with me here, and this R group attack, and then I form a new bond here. You can see how this swing left and right. Okay, thank you very much. All right, give them a big hand. So you understand what I mean by swing left and right? This is what happens in olefin polymerization. So now we understand this. Let's take a look then. When we have the olefin coordinating, you can look in my hand like this. This is the double bond. Okay, this is the double bond there. My thumb is actually the metal group, the R group there. Okay. So imagine when you coordinates to the polymer chain, the R group can be either up or down, right? See, the R group can be this way, or the R group can be this way. This is how it coordinates. Okay. But when you look at this, the R group, there's nothing on this side. The bottom one, there's also nothing on this side, so they look very much the same, right? So there's no preference at all. It's the same, either point this up or point this down. So it's really the same there. But when you have different R group, for example, the top metallocene has larger group on this side. The R group will feel different environment, because now if the R group is pointing up, the thumb will hit with the big group there. But if it points to the bottom one, okay, this is much better, right? Because there is no steric hindrance. So based on this analogy, which one should be more preferred? The left or the right? The right one, right, should be more preferred, because less steric hindrance. This is how we control selectivity in metallocene. Okay, and another thing is that metallocene, like cyclopentadiene, one good thing about it is it's stable. But one bad thing about this is CP can fly. Okay, the CP ring, just like helicopter. You see the helicopter, right? I mean the blade, it flies around like this, right? Same way here, the CP ring can move around like a helicopter. So that means if you have if you fix this on top, the bottom one can move left, right, anywhere it wants. So in terms of selectivity, this is really bad, right? Because usually, normally we have, nothing on this side, but suddenly now the selectivity change. So we don't want this to happen. The way to solve this is, why don't we lock them up, tie everything up so that there is no rotation. See, if we tie the two rings together with some metal group, like a CH2 group, or maybe silicon, if you tie them up, it's locked, so no movement anymore. If there is no movement, then we can control selectivity, so that the ring will not fly around. Right, now let's take a look at how we can control it. You take a look at the C2V symmetry point group. What happened? You can imagine yourself. You are like a guy. This is the catalyst approaching this side or approaching this side. Let's start with the left hand side first. You are a person. Okay? Imagine I'm walking. Okay, my left hand or my right hand here, they are the same, right? No difference between this or this. So that means there will be no selectivity on this side. Okay. If I walk on this side, you can see the left or the right is the same thing, right? So that means if you are a monomer, there will be no selectivity at all. What you would get after polymerization, you will get atactic polymer, because the first one comes in, no selectivity. The next one, still no selectivity. Next one here, no selectivity, right? The next one, no selectivity. So it's random or atactic polymer. Same thing for something like this, no selectivity on this side, right? And when you come on this side, even though this is big, but they are the same magnitude. So still, no selectivity left or right, right? You get atactic polymer for the catalyst that looks like has a structure like this. But what about something like this then? C2 symmetry. If you come from the left hand side, which one is more preferred? This is more preferred, right? Methyl. Because you can see nothing here, but well, this is large group, so your left hand side is empty. So yeah, left hand side is good. But now if you go to this side, you can see that still the left hand side is good, right? Nothing, this is big on the right hand side. So left hand side all the time. So if I transfer to selectivity, it means if this is up, it's going to be up, 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 up all the way. So when you have methyl group pointing to the same direction, we call it isotactic. Iso means the same, right? Isotactic polymer. What about some CS structure like this one? CS structure, if you go from this left hand side, from this side, you can see left hand is more preferred, right? But now, if you approach on this side, left hand is not preferred now because this is large, but this time it is right hand, right? Right hand side. So it will be up on one side. When it moves to the other side, it will be down. And then go back to up, down, up, down again. So we have a symbiotic polymer. This is how you can design the ligand and then use it to control the selectivity. Let's take a look at real example then. You see, this is isotactic polymer. You see, from this side, you approach this angle. The two CP ring are linked by CH2. Okay, and you approach this side. Okay, right hand side is empty, right? Right hand side here is good. If you approach here, hey, still right hand side is good. So it will be the same. Up, 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 or it can be down, 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 down. It's the same thing, right? See? Or even this one, you approach from this side. Well, it's tough to say. I don't know which one is larger between methyl or the aromatic here. The reason I say I'm not sure because methyl occupies larger space in 3D, but this is planar. Even though it looks large, but it's planar. So not sure which one is better, but you can imagine. Let's assume this is larger. That means right hand side is good, right? When you move on this side, it's the same way. Right hand side is good. So yeah, you can get the isotactic polymer. Same way for this one. CS for syneotactic. In this example, they linked the CP together with CR2. R can be anything, met2, a proton, many other things. But the point is, if you approach on this side, left hand side is available. So left hand side is good. Left. Approach on this side. Now the right hand side is good. It will be left, right, or another word. It's the syneotactic. Right, up, down, up, down, and so on. Okay, same way for that. Now what about something that looks like this then, C1? How can we identify this? If you go from this side, what happened? Left side is good, right? Left side is good. If you approach on this side, what happened? It's the same, right? Left and right here, see, it's the same. So it can be random. Right? That means on one side it's up. The next one is random. Okay. Next one is up. Next one is random. Hemi-isotactic. So if you understand how the structure relates to selectivity, then you can kind of, it's predictable. When you look at the structure, okay, this is predictable. It can cover I would say 80-90%. There will be some exception. Okay, sometimes you design the catalyst like this, but maybe the steric hindrance is not enough, so still not selective, for example. That can happen as well. Hemi-isotactic. Same thing as C1, you can use the same analysis to get hemi-isotactic. Okay, I always put this thing here. See, assume no site epimerization. What does it mean by assume no site epimerization? Does anybody know what epimerization is? Site epimerization means you scrambling the site. You are scrambling something. Okay. Imagine. Remember the example I brought the guys down here. You have to switch between left and right, left, right. But in real life, this is ideal, okay? What happened was ideal, but in real life, there will be some small percentage. What happened is, the polymer is here. This is empty. But before the new monomer comes in, this R group just move to the other side. Okay, this is called epimerization. Okay, site epimerization. The site is epimerized or moved to the other side. This happens, but small percentage. When that happens, you kind of screwed up the whole thing, right? Because rather than up, random, up, random, it could be up and then up again before it is random, But like I said, assume no such thing happen. But just want to let you know that site epimerization may occur in some catalyst system as well. But normally it does not. It will follow really, left, right, orientation. But let's say if you do polymerization at 1 atm, for example, small amount of ethylene. Ethylene may not feed in time. Before this thing can come in, ethylene doesn't come yet, so this thing just, why don't we just scrambling, play around. So there are many factors that control actually the site epimerization. All right, here, okay. I talk about the site control, okay. And other thing is, there will be some case where it's totally asymmetric, Nothing are similar, like this one. Okay, this group may be easy because this part is low, less steric index, but this one, who knows? We don't know, right? For such case, then we may have to really do experiment to see what's going on or what would be the product. Like this one, sometimes it's difficult to determine. Okay, hemi-isotactic, here are some example of the hemi-isotactic. Okay, that's the ligand control, okay? But what about the chain end control? You see, this is the ligand. This is the chain, polymer chain. If you want to control using the ligand, that means we put some R group in the ligand, right? But when you look at the chain, polymer chain, you see this a star here. This is the R group, methyl group, and we have proton on the other side. This is chiral, right? See? when we say chiral, that means the 4 groups on carbon atoms are totally different, right? See, this group is different, this group is different, methyl group, proton there. So everything here is different. That means this is chiral carbon atom. So when this chiral carbon atom is next to the metal, that means the new monomer may be influenced by the chiral center as well. So this chain N, this is the chain N, this is the polymer chain, this is the N, okay? So they call the chain N control the polymerization. And to understand what's gonna happen for the chain N, it's totally random really. It could get like isotactic, it could get syneotactic. Sometimes it doesn't show up, you know. So it's still quite unpredictable, not random, I mean unpredictable in the sense of which way it will control. In olefin polymerization, it's one way. In lactide polymerization, a lot of time you get syneotactic preference, you know, something like that. So that's still unpredictable, all right? Okay, and some other ligand systems where you just have to really, can't really predict, but then later on you just have to do the experiment. Okay, another thing that the last part I want to mention about homogeneous catalyst is in 1990s, when Sigma and Netta reported the titanium catalyst here, they got polyolefin, okay, polyethylene as a mixture. And then with his clever method at the time, he used the mixture of the polymer, okay, and dissolve it in acetone or diethyl ether. And he found out that there will be some part that is soluble, okay, in acetone or ether. And then he found out that it is the atactic portion. Remember I told you when you have crystalline, the polymer is strong, right? Atactic, the polymer is not strong, it's soft and soluble in many organic solvents. So the atactic part is soluble in ether or acetone. But highly isotactic portion will be insoluble in mostly anything. If you have heptane and then you reflux it in heptane, some of them will be dissolved, some of them still there. Okay. What is insoluble in refluxing heptane is called the isotactic portion at the time. But sometimes, you know, we have a partially crystalline portion, a mixture kind of between the two. Okay. It's kind of, you know, better solubility, but not as much. If you can isolate that, it is intermediate solubility or partially crystalline portion. A lot of industry are focused on this one because this is a flexible thermoplastic. So when we talk about thermoplastic, that means we heat it up, you can mold into different shape, cool down, you get the new shape, right? So it's quite useful in terms of practical application. So thermoplastic elastomer, yeah, people got interested into here. So how do we make it then? Later on we found out that partially crystalline portion comes from isotactic and atactic mixed together. The point is, as a chemist or if we are dealing with catalysts, how do we design a catalyst so that we get a mixture of isotactic and atactic together? Not like alternating or anything like that, but maybe block of isotactic, block of atactic, but within the same chain. Okay, this is more challenging at the time. So what people did, okay, one approach is, why don't we use the side epimerization? Okay, the one I just mentioned, side epimerization. Let's say when you look at this one, if the polymer is on this side, you can see one side, it is specific, right? That means the catalyst can polymerize in a random fashion here. So if it polymerizes on this side, it is atactic polymer. But if the polymer is, where is it? Okay, polymerize here. Okay, polymerize, you get a specific state, which is like a random polymer. You see this? But now if the side epimerization occurs, it moves to the other side, so that the monomer comes in and influenced by the R group here. This R group is lower, this R group is like a small, larger and smaller. So you will get one side which is random, the other side is kind of isospecific. So you will get different block of isotactic polymer and atactic polymer on the same chain. Okay, this is one concept, but the thing is, it's very difficult to control the epimerization. Like I said, sometimes it happens, so quick, and we can't really control it. For those of you who don't understand, okay, let me explain the site epimerization again. This is the empty site, right? This is the empty site. Before monomer comes in, the R group switch site epimerization occurs. Before ethylene comes in, or propylene comes in, this group moves to this side, and now you can see it's random, right? So when this happens, it will always get atactic polymer, and then you get atactic polymer. But now, if it moves into the isospecific side, this one, before ethylene comes into this side, this group will always move to this end. So you will get selectivity one side to get isotactic part. Okay. I have to re-explain because I can see the question on your face that doesn't make sense. Now you understand, right? Before ethylene comes in, this thing moves to that one. But a better way, Jeffrey Code, some of you may notice this his name. Jeffrey Code with Professor Wemit reported in Science in 1995. He used this idea actually, which is very clever actually, because you see he made this complex CP in the middle, and then you have benzene ring here and the phenyl group on this side. And as I mentioned, this group here, it can rotate, right? It can move around. Okay. So what happens if you look to the structure like this one? What would be the polymer produced from this catalyst? If you go to this side, it's the same group, right? Atactic here. If you go to this side, same group, atactic, right? So random basically. So this catalyst will produce random polymer. But let's say if the CP ring fly around like a helicopter, change to the different position into here. This group, I don't know which one is bigger, but yeah, it will have to select one. Let's say this is bigger then. Smaller here, when it moves to this side, smaller on this side, you will see that this is isospecific, right? So when on this side you get atactic polymer, when it switch to the other side, you get isotactic polymer. So you ended up as a block of atactic, isotactic, atactic, isotactic. This was the first idea that used oscillating catalyst, That's why it's published in Science. A big news actually at the time for Jeff Code. He's in Cornell University now. What else? Another technique that people use is called the chain transfer. Maybe if you use the oscillating catalyst, it looks complicated. And a lot of time, how can we control this? The rotation, it's quite difficult to control, right? Or how about if you want to continue like one bigger part of this, smaller part of this, then it's very difficult to control. So people think, oh, how about this technique then? We use chain transfer instead. If we want isotactic and atactic all together, why don't we just add two catalysts? One catalyst make random, one catalyst make isotactic polymer, two catalysts, and then we just add the chain transfer so that it polymerized and then suddenly switch to the other one instead. So we make we make random, right? Suddenly switch to isotactic, or isotactic after a while switch into a new catalyst. So it will be block of isotactic, block of atactic altogether. It's quite a good idea. See, from here you have this catalyst, right? A specific makes you random, and then this group is transfer switch, basically switch to give you this. See, this is switch here, this is switch there, and after you do more polymerization, actually isotactic is now added with the random, and then you will get kind of a block of isotactic and atactic. actually this is quite a clever idea. I think the way they do it. Okay, and many other things afterward. Right now there are so many techniques that you can play around. For example, I think this is the last slide I show you, right? Okay. Another technique that people use is imagine if you want to make softer polymer, okay, like flexible polymer. Normally what people do is you get polyethylene, right? You have to copolymerize with hexene or octene so that you get like a long chain of ethylene and then short chain of hexene group, along the way. And when you have kind of a hanging group like that, the polymer will be flexible and soft. Okay? To make these materials, you need to copolymerize two things. Ethylene, that's one thing, and then one hexene, that's another thing. So that you copolymerize, you will get a tiny group attached to it. There was one group that say, if you want to do that, then you have to intentionally add hexene, right, in there. How about if we make the catalyst that can oligomerize, change ethylene into one hexene on the fly, and then you have two catalysts. One catalyst copolymerize, and another catalyst does not polymerize, but only oligomerize, trimerize. Ethylene change into one hexene, and when one hexene is produced, this will be coordinated or copolymerized immediately, on the fly. The way to make this happen is you must link the two units together so that it is in close proximity. If you add two catalysts, they don't see each other, right? But if you link them covalently bound, like this one, when this polymerized ethylene, you get polyethylene, and then this make one hexene. When one hexene is produced, it got incorporated immediately. So that means you just need only one monomer, which is ethylene, to produce, branching polyethylene. So this is also like a very clever design, but still, as the industry, they don't care. Like, oops, catalyst is gonna be a long synthesis, long design. It cannot touch air, cannot touch moisture. Okay, I'll forget about it. I'll just use cyclonepta, which is cheap, abundant. Any worker, like a low skill worker, can still do the job. It ends up like that. It's so sad, as the scientists, we develop a lot of fancy catalysts, but then the industry say, okay, it's too fancy for me. Can we develop something like this? Can I have something like this, that can still make the product in a cheap way? Okay, so I think right now I pretty much explained or introduced you into the homogeneous catalysis. Okay, like I said, both of them are good in different ways. Okay, I'm not saying homogeneous is better than heterogeneous or vice versa, but it's just depending on what you're working on, what kind of catalyst. Deoxygenation or dehydration, zeolite is the best, industry. Take out water from ethanol, for example, like the one that Ajahn Chularat is working on. Yeah, you have sugar convert to ethanol, and ethanol dehydrate and then becomes ethylene. Zeolite is the best, I agree. Homogeneous doesn't do as well, but afterward polymerization, maybe homogeneous is better, So really depends on what you're working on. But the point I want to make is when you talk about homogeneous catalyst, selectivity is what is best known for. People got Nobel Prize twice now for chiral catalysis, in catalysis, the Nobel Prize. Yeah, that's a homogeneous catalyst. Okay, so any questions before we break up? That's it for the lecture today. Okay, if not, then thank you very much. Thanks everyone for staying with me. Okay, so next week we'll come back toอาจารย์จุฬาลัตน์ Alright สวัสดีครับ ขอบคุณมาก ถ้ามีคำถามก็มาคุยกันต่อได้